Hi, Melchior. To start.
Ja, ik kijk gewoon direct erin.
You're live, Melchior, so we can hear you.
Okay, perfect. Hello, everybody. Welcome to this third Belgian session on the FIRS framework, which is a cost-benefit analysis tool for fire, life safety, and business continuity. I myself am Melchior Schepers, project manager at Fire Engineer Solutions Ghent, which is a consultancy firm specializing in fire safety engineering. And this project has come about in cooperation with the University of Ghent, and more specifically, thanks to the involvement of Professor Ruben van Coile and Professor Tarek Beji. So what is FIRS exactly? FIRS is actually an acronym which stands for Fire Integrated Environment for Risk Comprehension and Evaluation. And basically, it's a probabilistic risk-based framework for the design and assessment of fire safety in tunnels. It started out in the beginning of 2020 as a research project. It's still ongoing, but it's nearing completion. And the incentive actually was that there was no broad Belgian quantitative risk assessment framework or even probabilistic risk assessment framework for fire safety in tunnels. As I said, it has come about via a cooperation with the University of Ghent, and it's partially funded through VLAIO, which is the Flemish Institute for Innovation and Development, which is part of the Flemish government. Let's talk about some background first on risk assessment frameworks, and after that, we'll dive into the FIRS framework itself. So in Europe, there are a lot of risk assessment methodologies available. You can see in the table that there's a wide array of risk assessment frameworks, them either being prescriptive or deterministic. Also with different levels of complexity, they can involve CFD, complex evacuation software, or they can vary to simple spreadsheets. But there are the applicability of a certain risk assessment framework, which might be very relevant in a certain country, might not be so applicable to another country. For example, a country with a lot of really complex long tunnels, the risk assessment methodology used over there might not be so applicable in Belgium. One of the things that most of these risk assessment methodologies lack that are currently used is important monetary considerations. So they don't provide an objective comparison in terms of cost of certain measures that need to be taken. Also, some of these date back as far as the beginning of the 2000s. For example, some used in France date back to 2003. So if we look at a typical approach in a risk assessment framework currently, we can say that really often a deterministic risk assessment approach or worst case approach is used during the design of tunnels, which basically means that, for example, we'll assume 3 fire locations, the beginning of the tunnel, the middle of the tunnel, and the end of the tunnel, with 3 fire sizes. For example, a relatively small fire, a car burning, let's say, 5 to 10 megawatts. A bit of a bigger fire, 50 megawatts for a heavy goods vehicle, and then sometimes we even consider a very large fire, for example, a dangerous goods carrier, up to 200 megawatts. If we then also consider 3 ventilation scenarios, transversal ventilation, longitudinal ventilation, semi-transversal ventilation, and really quickly we end up with, in this case, for example, 27 cases, so 3 times 3 times 3. But then the question arises, what about electric cars? What about hydrogen? What about CNG? What about LPG? The lifespan of tunnels, we can assume it's more than 50 years. Is it sometimes, or nowadays, even 100 years? How is the traffic density going to change in the coming years? How is the composition of vehicles going to change in the next 25 to 50 years? Those are all aspects that are currently not taken into account in a lot of the existing risk assessment framework. And also, what about the probabilistic nature of a fire and the related consequences of fire in itself, or is inherently probabilistic in nature? So these were the incentives to come up with a new probabilistic risk-based framework, which is FIRS. So what are the focal points of this framework? Well, we wanted to evaluate the effects of fire safety measures on different aspects. It being life safety, of course, one of the most important aspects in fire safety. We want to get people out safely out of the tunnel, but also in terms of structural safety. Of course, we don't want the tunnel to collapse. Want to look at what if a fire occurs, what is the expected damage, so the level of damage is the metric we've defined. In terms of business continuity, if it's a really important tunnel in your road or transport network, you don't want it to be closed for weeks or months even. And then also the measures that you define or that you propose. What is the investment cost? What is the maintenance cost and associated to that the reliability? And what is even the repair cost of your tunnel or your equipment in case a fire does occur? So what we've devised is really an integral framework which focuses on decision makers. And the goal is to set out clear performance metrics for the authorities and provide them with a tool to objectively quantify design decisions. The idea here is as well to span almost all possible scenarios because we take a probabilistic approach and a continuous set of distributions for all boundary conditions and all things we consider. So how is the framework itself composed or built up? It's basically built up out of 3 interacting layers, layer 1, layer 2, and layer 3, as you can see here. So in the most basic layer, the first layer, we have really the defining events of a fire. That is the ventilation, so how is the smoke gonna spread throughout the tunnel? Evacuation, how are people gonna evacuate? How many fatalities are there possibly in case of a fire? And then really importantly for the entire framework, the probabilistic nature or considerations of the boundary conditions. For example, we just take a continuous distribution for the fire size and we assume that it's, for example, a normal distribution around a certain mean, and we take that entire set, so from 0 to 200 megawatts, let's say. Also in terms of wind, it's probabilistic. Once again, we consider the location of the tunnel and look at what the probability is that there is a certain wind direction or a certain wind pressure at the portals of the tunnel. In the second layer, we've got firefighter intervention. We've also got measures. So which are the measures that are taken into the tunnel? Is it active measures? Is it passive measures? For example, sprinklers or fire-resistant boarding inside the tunnel lining. And then we also look at fire development. So how is the fire going to spread inside the tunnel? And then in the third and final layer, we look at traffic effects. What's the composition of the traffic going to be in coming years? We look at the integration of the control. So when do we activate ventilation inside the tunnel? And last but not least, the cost is also considered in that third layer. So these layers are all built up out of their own submodules, which interact on a high level via exchanging inputs and outputs. If we dive into those layers, we can see that the first layer, as I said, included ventilation, evacuation, and the boundary conditions. So first things first, those probabilistic boundary conditions are considered as a set of continuous distributions. That means that we consider an entire range or distribution for a certain boundary condition. As I said, wind pressures, which can change, heat release rates, for example, the composition of the traffic are all considered as continuous distributions, which are then sampled and used as inputs for the calculations. The ventilation model itself, that's a proprietary 1D finite volume model, which was developed in-house. And then there's also a 1D in-house network model for evacuation, which helps us evaluate the FED and the FEC of occupants inside the tunnel. Then in the second layer, we've got what we've called the fire brigade intervention model. This model takes into account the firefighter intervention time or expected firefighter intervention time, which then also interacts with the fire development, which is in there as well, so the fire spread model. If there's a fire in the tunnel, what's the likelihood of the fire that it's going to spread to multiple cars? What's the likelihood of it spreading to a heavy goods vehicle? And then the interaction with the fire brigade intervention model. When are the firefighters expected to arrive, and how are they going to tackle the fire? Really important here, of course, is as well the interaction with the measures that are proposed. If there are sprinklers, what's the effect of sprinklers on the smoke gases? Are they going to cool the smoke gases? What's the effect on toxicity? If there's passive protection system, for example, fire-resistant boarding, we can expect the smoke layer to remain hotter for a longer time. Smoke is perhaps going to travel further down the tunnel, upstream, downstream of the tunnel. So those interactions are all taken into account in this second layer. And then in the third and final layer, we take into account the effects that are even higher up the levels or less basic of events than the fire itself. This is, for example, the traffic effects. Can we expect there to be a lot of traffic jams in the tunnel? The density of traffic is going to affect the amount of occupants in the tunnel. There's also going to be an effect of the amount of new energy carriers. We want to look at the distribution of electric vehicles in the future as well. So that's once again taken into account in a probabilistic way via those continuous distributions. What's in there as well? The control of the ventilation system. Of course, when we switch on the ventilation system, it's going to have an effect on the smoke spread. So that's taken into account over there. And also the goal is in the future to have a hardware in the loop solution where we can really integrate the real life tunnel with our own models. And then last but not least, in the third layer, also cost is a really important aspect. Not only investment costs, so what is the cost of the proposed measures going to be, but also the maintenance cost that associated with that reliability. Sprinklers might, for example, be much more reliable than jet fans that are not properly maintained. In terms of business continuity, how much does it cost if a certain solution is proposed and there is certain damage if a fire does occur? So that's that level of damage that we've defined over there. If a fire does occur, what are the expected damages and how much is it going to cost in terms of business continuity and repair costs to repair those damages? Now, nevertheless, any risk assessment framework, uncertainty is always a really important factor. And that's of course the same here in the probabilistic approach. There's always three main factors of uncertainty. We've got parameter uncertainty, which we try to tackle here by using continuous distributions, which are then sampled. We've got model uncertainty. We're using our own in-house developed models. Those will be validated using accepted tools or existing software, for example, CFD tools, existing evacuation software. And then there's also completeness uncertainty. For example, you don't know if your model takes everything into account. In this case, this can, for example, be that we don't take into account explosions or certain biological risks, for example, chemical leaks, etc. Now, the key to these uncertainties is to do a good sensitivity analysis, and this sensitivity analysis is a key aspect of the framework as well. I've got a small graph here in the top right corner, which tries to just give a really brief overview of the sensitivity. What you see here is a sensitivity of a full tree, with 6 branches to certain with a sensitivity on the final frequency of the occurrence for every split. And as you can see, that certain branches affect the final probability of something occurring much more than others. So in terms of measures, it's probably much more effective to take into account or to take measures to mitigate these branches rather than these here in the middle. At the lower right, you can then also see an example of the distributions we take into account for the input parameters. So what are the main takeaways from this presentation that you should take home to your work? Well, the first framework we propose is a probabilistic risk assessment framework, which consists of 3 interactive layers. And the goal is that the framework provides an objective trade-off between design decisions, either be it at the beginning, at the design of a new tunnel, or during the lifetime of the tunnel, during refurbishments, and it's specifically aimed at providing decision makers with really an objective with objective metrics in order to design which measures to take. And I think we've nicely reached 15 minutes now. So if there are any questions, I'd be glad to take those.
Yes, indeed, Melchior. There are two questions in the discussion forum. First question of Hendrik Bijland. How would you describe the knowledge-based supporting definition of probability distributions and effects of measures such as fire department involvement?
So I'm not entirely sure if I get the question correctly, but I think there are a couple of things. First of all, of course, what's really important here in this approach or in a probabilistic approach is the statistical data that you have. You'll need to either base that on data from other countries, data from your own country, look at historical data, look at literature reviews. So that's, of course, a really big aspect of it, and that's a big aspect of the work we've already done. And then on the other hand, in terms of firefighter department involvement, big or important aspect there is, first of all, just talking with firefighter or with firefighter houses and getting their standard operating procedures, and then looking into their intervention times, data on intervention times. And then we also take into account the distance of a firehouse to a certain tunnel. So those are all things that are taken into account and which are actually based off of a previous research project as well, which focused on firefighter intervention in parkings. And so now we're changing that model a bit to take into account firefighter intervention in tunnels.
Thank you. Next question coming from Urs Grönicke. What have you found to be the governing scenario, a rare catastrophic fire or the more frequent smaller fire incidents?
Yeah, that's a really good question, and it's related a bit to the concept of tolerability. So it's really hard to say what the governing scenario is. In a deterministic approach, that is often the worst case scenario where you say, I want to mitigate this scenario and we need to take action to it. Now, in a probabilistic approach, the trade-off you make is what is acceptable and what is not acceptable in terms of measures. And you also look at the frequency of their occurring. So it could be that there is indeed a very high consequence scenario with a very limited frequency. And then we're going to look at what's the possibility of it occurring and can you live with those consequences? So that's the concept of tolerability. In a perfectly rational world, you would just make a cost-benefit analysis, and that would be it. But here, we also have got to take into account that with the measures you define, you need to be able to live with the consequences as well.
Next question coming from Tom Otten. Are you familiar with the quantitative risk analysis developed by Rijkswaterstaat? If so, what are the important differences between FIRS and QRA 2.0 of Rijkswaterstaat?
Yeah,
what are the advantages and methodologies? Are they comparable?
So as far as I'm aware of, the QRA method used in the Netherlands, indeed Rijkswaterstaat, is based off a bit more simpler models, I would say. It definitely has its advantages and its usages, but also has some shortcomings in terms of ventilation strategies that can be used. For example, transversal ventilation, if I'm not mistaken, is not taken into account. So those are all things that we can take into account in our own models and that are taken into account in the trade-off when proposing measures. So the model, or the FIRS model, is quite a bit more, quite a bit broader, I would say, in taking it into account the possibilities in terms of designs that are possible, also in terms of fires that can be considered, and in terms of evacuation model even as well. So I don't think they're really comparable, and that FIRS is a bit broader than the Rijkswaterstaat model at this moment.
I'm sorry to interrupt you, Melchior, but we
Yes.
have to go to the next session. If you want, you can always come back to this session and type your answers to the remaining questions. Okay,
perfect. But thanks everybody then for joining us.
Thank you, Melchior.